Hi guys. So I think it's probably a good time to start this session. So just as a heads up, there are going to be two of us speaking at this session. Myself, I'll be talking about my progress with Hadoop HDFS optimizations, and shortly afterwards, Owen will be talking about HipHop porting on V8, I believe, as well. So we're going to, about just before past, we're going to do a context switch, or a little bit of a context switch. So essentially, I've been doing some preliminary analysis of the performance of Hadoop on ARM. Now, I've concentrated on low-hanging fruit, i.e. what can we do right now, what is obvious, what optimizations will be unambiguously preferable. So at the moment, I've been reducing the CPU-bound tasks, which should be reduced. As the storage on Hadoop underpins pretty much its entire operation, my attention has been focused on the HDFS cluster file system. My experimentation has taken place against version 2.0.2 alpha because that was the most recent, stablest version that I could see. There are various different versions of Hadoop out there, so if anything looks a bit strange, it's because it's Hadoop version 2.0.2. Hadoop 2.0.3 is either out or coming out. It's pretty much in the process of being released. And just to reiterate the message that's been conveyed in the previous session, these are preliminary optimizations. They're optimizations that made sense to us to look at the beginning, but they're not real-world optimizations necessarily. So we really are interested in hearing about real-world usage. We really want to know what annoys you guys when you're running things like this on ARM servers, because the best way we can optimize is optimize realistic workloads. If we spend too much time optimizing something superficial, we're wasting everyone's time. So the Linaro Steering Committee is a good place to talk to. If you go via that for your contacts, and we can then get the information and work on more sophisticated optimizations as well. So I'm just going to do a very quick heads up on the distributed file system. Hadoop itself is quite a complicated system that's inherently distributed. It consists of lots of different nodes. These nodes all communicate and perform tasks. You have nodes that have specialist purposes, and these all run on a massive cluster of machines. So specifically with the file system, we have some nodes that I'm going to mention now. The most important node is the name node, and the name node essentially holds all the metadata on the file system. What are the files called? How big are they? Where are they? That sort of information. And you can only have one active name node per namespace. So you typically have multiple namespaces running, and each namespace has its name node running. And of course, that gives the name node a high memory requirement. The most common kind of node are the data nodes, and the data nodes actually store the file system blocks. The block size by default on Hadoop is 64 megabytes, so those of you used to 4 kilobyte blocks, this is essentially because Hadoop's designed for big data. It's not designed for 10 kilobyte text files. It's designed to really crunch data down. And you've got some optional nodes as well. You can have passive name nodes to try and mediate against single points of failure. You can run high availability configurations as well, and the HA stuff is reasonably new, but I'm just going to say it's there. I've not really explored it. I've just been concentrating on raw data performance on a very basic HDFS system. Also, it should be stressed that data nodes have a notion of topology about them. So data nodes usually know which racks they are in, and they'll try and distribute data amongst themselves to mitigate against failure of a rack. And they inherently distribute blocks of data automatically because a data node can crash, or a data node can become unavailable, or the storage can degrade. So data on a HDFS file system is typically replicated automatically. So there's a lot of data transfer going on. So nodes can run on the same machine or different machines. So it depends upon the actual workload of a particular node. You can have, for instance, high availability node coupled with a data node. Typically, one would have a name node running on its own system because the name node has usually got quite high resource requirements. So because the whole purpose of HDFS is to provide data and mitigate against failure, there are a few safety mechanisms in there. So metadata on the name node can be archived to multiple file systems. You can take snapshots of this as well. And if you have a catastrophic failure on the name node, you can recover from your snapshots. You can also have HA configurations where you've got special journal nodes that maintain a quorum of metadata rights. And this allows one to bring up a name node very quickly because it uses the data in the journal nodes. This is a reasonably recent thing. Now, most of the focus of my talk today is going to be on how the data integrity algorithms work in the data blocks. So data blocks are essentially transferred between data nodes because we have to replicate the data amongst them. Because we're shunting data around a lot, we have to maintain its integrity. We have to be confident that it's correct. So there's a heavy usage of checksumming, and the default checksum algorithm in Hadoop out of the box is HRC32C, and this usually operates on blocks of 512 bytes. So as a preliminary first step for optimization, I've constructed a basic test configuration to test the data read and write paths. So at the moment I've been working on one machine, and on that machine I've run a name node, a data node, and a workload, a test workload. The test workload essentially just being the benchmark itself. The benchmark is a built-in one. It's called testdfs.io, and the testdfs.io is one of the unit tests built into Hadoop, so everyone's got access to it. Just to reiterate what I've said, it's not a real-world workload. It is a synthetic benchmark, but this is just an exercise in grabbing the low-hanging fruit. I've operated on an A9 platform, and I've used the latest Softload Oracle JDK because Hadoop itself is a Java application. It runs on top. It runs within a JVM. To measure performance, I've investigated the performance from Linux perf to get an idea of how things are shaping in kernel land a little bit. And to actually see inside Java land, I've run the inbuilt Java profiler. It's the basic out-of-the-box one. There are other Java profilers out there, but all Oracle JVMs have a built-in HProf, which at least gives us a notion of where we are inside the JVM, which objects in Java and methods are using up the most CPU samples. I've got some information from the perf results and the Java results. I've put these in the slides. I'm not going to read out every single line. Essentially, I'm just going to give you an indication. This is roughly what I've been gathering. I've got more information at the end of the slides, and the slides are accessible from the Linaro Connect website. So I'm going to go through this reasonably quickly because I'm conscious of taking up too much time. But the slides are online. Please do read through them if you want to see more information. I've highlighted here the testdfs.io write test, which is essentially write a 10 gigabyte file in this particular workload and tell me how quickly you can do it. And the workload will then communicate with the name node and the data node running on the same machine and try and get that file written. It'll then perform the necessary integrity checks as well, because that's native to Hadoop's operation. I've deliberately chosen the name node Java samples here, and if you can't, sorry? It's running, the question was, what am I running the name node on? I'm running the name node, the data node, and the workload on an A9 test machine. So they're all on the same machine. I've deliberately put the name node Java samples on to show you the name node is not doing anything. It is waiting. So this is a synthetic benchmark. It isn't a real-world test. In real life, the name node is going to be under a lot of stress because it is looking after a lot of data nodes. Linux perf results have highlighted some information here. And we can see from Linux perf, we're running 2 Java processes are taking up most of the CPU. And I've highlighted in bold some interesting functions that are taking up more CPU than I would like. And these are related to copying memory. We've got the user space memcopy, and we've got 2 kernel space memory copies as well. To make things easier to look at, I've graphed this up into a pie chart, and I focused my attention on a few very basic things. So all I really care about at the moment for this first path is how much CPU time is Java taking, how much CPU time is being dedicated to computing CRCs, and what have I got left over. It's very simplistic, but it's just meant as a first step. Now, I've got blue for everything else, i.e. leftover tasks that aren't attributed to running the Hadoop workload. I've got red for Java, and yellow for memcopy, and green for CRC. If you notice, there's no green on the left-hand side. On the left-hand side is the Linux CPU distribution of CPU for testdfs.io write. And essentially, testdfs.io write is performing all the CRC computation in Javaland. That's why the red is significantly larger. On the read test, we see a little bit of red and a lot of green, and the green is essentially the inbuilt native CRC computation, and this is the slice by 8 implementation. For those familiar with CRCs, it is the stock Hadoop code. So this is just compile out the box, run it, see what happens. And it's one of the fastest generic software implementations for computing a CRC. So, as I mentioned before, from the perf results, the name node's not doing much. This isn't representative of how things work. I've got some more data at the back of these slides that you can look up, but I'm going to just go through a summary of that data. When writing data, we spend most of our time in Java, and we're actually inside the pure Java CRC32C class running the update function. And this is essentially incrementally updating CRCs as it gets data and then storing it. When reading data, we have a slightly different performance profile. Most of the Java time is actually spent asking the native method, please verify these CRCs, and most of the CPU time is in the native method, which is the slice by 8 software implementation, the generic C implementation. And I'm going to keep mentioning memory. About roughly 10%, a little bit more, is spent copying memory. So work has been carried out to optimize the read and write paths in Hadoop. One of the best notable patches I've seen is by Trevor Robinson from Calzada. He's submitted a patch which cleans up the entire write path. And this basically uses a slightly different set of data buffers in there to avoid memory copying within Java. And it does speed things up on ARM, and it also usefully speeds things up on x86 as well. But that's mainly Java code optimization. I have been working on speeding up the computation of CRC32C using Neon, intrinsic Xen assembler. Also, I've done some very preliminary experiments on trying to replace that pure Java CRC32C with a native JNI wrapper, because I don't think Java should be spending its time doing a basic task. We need to give the CPUs enough time to actually run the proper Hadoop workloads. So my focus is essentially trying to get the CPU to be free as quickly as possible. I have a summary of my CRC algorithm online with a slightly better explanation and introduction of the methodology I used to compute the CRCs using Neon. As a rough summary of what I'm doing in Neon, I'm getting a data buffer and making it smaller with a series of transformations. The smaller data buffer has the same CRC as the original data buffer. So the idea is, by performing operations with Neon, I can make the data buffer smaller, quicker, and hand over to another CRC computation to compute the residue. So in the implementation I've been testing, I reduce the buffer by 32 bytes at a time in each loop iteration, and I'm left at the end usually with 32 bytes, which I then hand over to the slice by 8. So the slice by 8 does a lot less work. It's got a much smaller data buffer to operate on. So it's a very basic algorithm by reducing 32 bytes at a time, and the reason it is because I found most of the CRCs actually in use in Hadoop on my tests have been computed for 512 byte buffers, because that's the default configuration. This is roughly what the data fold looks like. This is explained in more detail on the wiki page, which is publicly accessible. So essentially, I perform 2 lots of polynomial multiplication, some polynomial addition, and I'm left with a magic message buffer m-x, which is smaller than mx, but has the same CRC. I'm happy to talk about this in length with people. Please find me, essentially, and I can go through this if there's any questions on that. To give a rough idea of the implementation, I perform polynomial multiplication in Neon, so that's vmul with a .p8 data type. I need at least 32 bits of multiplication, so I need to chain together multiple 8-bit lane polynomial multiplies. So as a rough idea inside the algorithm, there are 16 vmul p8s, which essentially is enough to wipe out 16 Q registers. Neon has 16 Q registers, so it's a bit tight, the register usage. So to try and, I've got an assembler version that performs the CRC buffer folding. Ideally, we should really be working with things like intrinsics, because intrinsics are a lot easier to understand, and the compiler knows a lot more about the processor that the end user of the code wants to run on, rather than the person that wrote the code on a different processor. So I've ported the code over to use GCC Neon intrinsics. It's really nice to look at, but at the moment it runs a little slower than the hand-optimized assembler. So I've got a test case, and I've sent that off to the Linaro toolchain working group, and the compiler guys in Linaro absolutely love test cases. So as an aside, if you're working on anything else that you feel is suboptimal, please let the compiler guys know if you believe that suboptimal code is being generated, because they really like test cases. So they're working on the intrinsics now, and they're going to go through. I'm going to quickly mention my work replacing the pure Java CRC32C class. This is the class that's used in the test DFSO write path. Essentially all I did was I maintained one of the methods, which is seldom called, and kept it Java pure, and the other method I just replaced with a JNI stub. So there's already native code in Hadoop, so I essentially added some stuff into the lib Hadoop library, and the new class essentially just calls into that. So, and I've chosen a horrendous name for it because it stands out in the sampling. So, the implementation I've come up with the test can probably be refined somewhat, because I deal directly with the Java type, which is the byte array. It may not be the best thing to do, because if you ask Java where byte arrays are stored in memory, you may not necessarily get the actual byte array in memory. You might get a copy of it that Java helpfully puts down for you, so that's going to slow you down quite a lot. I've used the primitive array critical, release array critical. There's a better way of doing this in Java using a byte buffer, and the byte buffer would require a reasonably significant refactoring of code. So that's why I've done it the quick way to test. But if we were doing this seriously and moving on with it, we would probably use a byte buffer. And the advantage with a byte buffer is we could be really clever with it, and we could actually allocate the byte buffer on an aligned memory address as well. So we could probably even speed up some computations. So I'm just going to try and keep things reasonably quick. So I'm going to put everything together and just show roughly what it does to the CPU distribution. So I've got 4 pie charts here. The top row is, sorry, the left-hand column is the original Hadoop code out of the box before I've added any changes to it. The right-hand column is the CPU usage once I've modified it. The top row is write performance, the bottom row is read performance. So again, you can the actual result I'm aiming for is to essentially make the blue bit as big as possible. So the blue bit is stuff that's not been attributed directly to the Hadoop workload. So on the first row, I've significantly reduced the red, which is the Java time, because I'm now using a new native class which hands everything over. I've also significantly increased the blue, so I've given the CPU more free time to do other things. On the bottom row, there's not much of a change. All I've done on the bottom row is change the CRC algorithm from the slice by 8 to neon folding. And the green gets smaller, which is good, because it's spending less time in the neon folding than it is in slice by 8, which is what I really expected. And the blue is slightly bigger, which is good, because it means there's more free CPU to do other things. So now we have in the patched code, on the write path and in the read path, most of the time is spent on native code rather than Java code. This then means when we actually do Hadoop workloads, we've got more CPU to play with. And again, we've reduced the amount, we've significantly reduced the workload in Hadoop on the write path, which again is a good thing to have. So, and again, I'm going to highlight we're still doing a lot of memory copying in both sets. So that's something that really should think about. So, reduce CPU usage. This gives us CPU cycles to actually do stuff with rather than just I/O testing. Hadoop itself is known to be very sensitive to underlying disk I/O though. So we need to think about the disks and the write paths to the disks as well. This is something I've not done yet because I've just been doing preliminary investigations. The other thing worth mentioning is Hadoop is a Java application, thus it runs a JVM. So it's a good idea to keep an eye on JVMs that are coming out, because the latest, greatest JVMs might actually give a decent performance uplift in certain scenarios. There is a beta hard float JVM that Oracle have on their page. If you search for, I think, Raspberry Pi Java, it's worth keeping an eye on, because it'd be nice to see if we get a hard float full release of the JVM. And again, the memcopy, I'm going to have a think about. Memcopy-wise, I know there's going to be some small changes in glibc to optimize, hopefully, to optimize smaller memory copies. So at the moment, glibc, as I understand, is very optimized for copying large amounts of data. Preliminary investigations I've found with Hadoop have indicated that quite a lot of memcopies are actually very small, typically of the order of magnitude of 217 bytes. So that'd be good to optimize a little bit as well. But before we over-optimize, we would really need to run some realistic workloads first, and then we can work out really where to do the rest of the optimization. Just points on hardware as well. For Hadoop, if we're doing a lot of disk I/O, we need to also think about the disks. So I've got a very basic test where you put an SSD in, and I've got reasonable performance uplift just by replacing the drive. So a factor of 2 on write and about a factor of 1.6 on read, and that's just by replacing hardware. Obviously, we can't just put SSDs and everything as a way to solve problems because, well, capacity and cost. But it's worth thinking about, at least for a middle ground as well when we're optimizing, because we could get a 10% optimization from software, but we've got to think about the entire thing as well. So that's essentially all the slide material I've got to talk about now. I've got time for quick questions now whilst Owen's setting up his laptop here.
Which version of Linux that you are using?
Sorry, can you please speak up?
Which version of Ubuntu or kernel that you
I used Ubuntu 12.10.
12.10. So it's again hard float.
It can run hard float, yes. Yeah. Are there any other questions? Sorry. Sorry?
Had you applied Trevor's patches when you were doing the benchmark or not? To
yes.
use direct buffers?
Yes,
oh, you did
they're
already.
really good.
Okay.
So it's worth having a look at.
So the benchmark that you have where memcopy also dominates?
Memcopy goes down a bit with Trevor's patches, but it's still high.
Yeah, okay.
So we've got other things to think about.
If stock Hadoop has a CRC implementation in its native library already, why are they only using it for the read part?
Okay, so Hadoop has a separate native CRC read, and that is essentially in the form of a bulk read, a bulk verify, which verifies CRCs of everything in one go. The writes path is incremental, and I think, well, I would presume that the writes path on perhaps the default platform of Hadoop doesn't really experience that much of a problem when it's writing. But we've noticed a sensitivity when running it in our systems. So it can benefit more than it perhaps does on other platforms.
Just really a comment on the memcopy. If you're spending 10 or 20% of your time in memcopy, the problem isn't memcopy performance, it's your architecture of your software. You need to cut the number of copies.
Yes, exactly. So essentially, that's what Trevor's tried to do, because the best memcopy optimization is to get rid of it. So we need to have a think about the kernel land memory copies, and we need to have a think about the user space memory copies as well. I've written a few basic unit tests to try and stress test the JVM to try and make it perform superfluous mem copies. I've not got anything good yet, but if I do get anything good, I'll forward it on. Are there any other questions, guys? Or?
Now, do you think the hard float will make any difference here? I mean, you said
yeah.
That there is a JDK 1.8 available beta version. Do you think that will make a big difference here?
For this particular workload I've been doing, hard float will make no difference at all. But there are other components that integrate within Hadoop that are more native and could benefit perhaps from the hard float interoperability. So it gives people more options as a good thing.
And just as a random comment about memcopy,
yeah.
We found that we got a huge CPU time boost by using a custom written version of memcopy that uses, what is it? It uses Intel's SSE instructions for copies greater than 16 bytes and just straight moves for copies less than 16 bytes. And a lot of implementations of memcopy for Intel will have lots of customization of this type for different sizes. I don't know to what extent that's been replicated on ARM, so that might be part of it.
Talk to Richard and some of the people. We do know there are some optimizations coming out which are for targeting ARMs. I think Neon Unit and VFP Unit for memcopy as well. But again, that needs to be precisely tested. But yes, it's in the works.
It's better on A9, but worse on A15.
Yeah, exactly. It depends what core you're running on. Yeah, so.
And it's true that customizing memcopy is a bit of a crutch, but it can get you some nice wins, I think.
Yeah. Yeah, so sometimes it might be worth multiple implementations, but it may also be worth trying to just get rid of it in certain cases as well. So both paths are probably a good idea to follow. Okay, shall we hand over to Owen for his talk? Because I think we're just about to hit 12:30. Again, please see me whenever if you want to ask more questions.
All right, my name's Owen. I work for Facebook, and I'm an ARM assignee. I'm working on porting HipHopVM, which is our PHP just-in-time compiler, to ARM v8. So here's just a cheesy little flow diagram of how the system is set up. To make it fit on the slide, I had to make it flow like sort of in a snaking pattern. It starts at the top left. You feed in PHP, we parse it, we do some AST level optimizations on it, and then we turn it into HHBC, which is our custom bytecode format. That's a pretty hard boundary. You can serialize HHBC to disk, and we do. That's how we deploy to production. So HHBC is meant to be machine independent, and is not meant to be language independent. It's basically a stack VMs, a stack-based virtual machines instruction set, where that virtual machine, the instructions basically correspond directly to PHP level source constructs. I have a slide at the end that shows you an example of it, if anyone's interested. So to run this, we enter a dispatch loop, which can dispatch to either a straight bytecode interpreter or to this other subsystem that constitutes the actual just-in-time compiler. The abbreviation HHIR here stands for hip-hop intermediate representation. We translate HHBC to this lower level representation, which breaks up HHBC opcodes into sort of finer granularity operations, and we do more optimizations on that. And then finally, we turn it into machine code. Our only target right now is x86-64, and then run it directly on hardware. So for the people in this room, the interesting part is going to be Hhr Codegen, the stage that transforms HHIR into machine code. So just a few more words about HHIR, just so we know what we're talking about here. The unit of compilation is a typed basic block of HHBC. What that means is that given a basic block of HHBC, that is single entry, single exit, chunk of bytecode, we can translate the same HHBC basic block to machine code several different times, depending on the combination of types that flow into it. So PHP is a dynamically typed language, so a single variable at the source level could take on any number of types at runtime. And we'll produce different machine code for each type that we see, for each combination of types that we see entering a basic block. And this type specialized machine code is how we get our speed up. It allows us to, it's a form of strength reduction, really. So HHIR is in SSA form and has forward control flow. Note, this is control flow within HHIR opcodes. There is no control flow within the bytecode that it corresponds to because we're only translating basic blocks. So first we transform to HHIR and then do some sort of compiler textbook optimizations on it, dead code elimination, deleting ref counts, eliminating dead stores, things like that. Then we do register allocation and then emit x86 instructions. This is just to give you an idea of the setup of the system that I'm trying to port. So this is generally the order that I'm going in. First, to get the interpreter running. And actually, yesterday, during the hacking session, it ran a hello world script for the first time. So the next stage is to get it running our command line test suites, which are basically just a whole bunch of little micro tests that exercise some of the stranger corners of PHP's behavior. There are many of those. And then probably to try bringing in some third-party code, some popular PHP third-party code base like WordPress, which includes both automated tests and a web app. Oh yeah, by the way, Hsvm has a built-in web server. This is how we run Facebook. After that, we can start attacking the JIT. First, things like an ARM assembler. Oh, by the way, we're only targeting ARM v8. We have 64-bit assumptions baked into everywhere in this code base. So for us, it's not worth it to try to adapt it to any 32-bit architecture. We also have a bunch of assembly little bits and pieces of code that get you in and out of translated machine code. And also some infrastructure for doing concurrent code modification. That is, one thread is executing some piece of code while another thread is modifying that code. We do this for a couple different reasons, and x86 is fine with this as long as the code that the instruction that you're modifying does not lie on a cache line boundary. And ARM v8 has some different conditions under which this is safe, and we're going to have to make sure that we're adhering to those conditions. And then finally, to sort of incrementally and gradually add support for just-in-time compilation to different HHBC opcodes. So we support falling back to the interpreter for HHPC opcodes that are not, for whatever reason, we haven't gotten around to implementing it yet, or it's not dynamically important enough, or it would just result in excessive amounts of machine code to fully implement. We can fall back to the interpreter for those cases. So we would start out basically falling back to the interpreter for everything, and then gradually increase coverage going forward. So what it's at right now, like I said, the interpreter can run hello world. I've tried to run a couple other tests from our test suite, and it crashes in interesting ways, so still some work to do. We're publishing all of the changes that I'm doing to get this to happen on our GitHub. Develop in the open, upstream first. And internally, we're also discussing design for this world where we have two machine code generators next to each other. And we have a few goals for this. Minimal impact on development cycle. Obviously, if you want to make a change to some early stage in the pipeline, we don't want all of our team to have to build and test on x86 and ARM, especially because we're only targeting ARM v8. There's no ARM v8 hardware. Simulators are slow. And we don't want negative impact on x86 code gen because obviously all of our site is running on x86 right now and will be at least mostly x86 for quite a while. So we still need to care about this. We're okay with having suboptimal ARM code generation at first because, I mean, at this point, we're still running in simulators. Performance doesn't matter. Once we get hardware, we can do performance tuning. So in addition, any strategy we come up with for having dual code generators like this needs a good exit strategy wherein we're not sort of painting ourselves into a corner with a bad design. We need to have a clear way forward to a world where we have two cleanly implemented machine code generators that generate good machine code. So that's it for talking about where we are right now. I figured we would have plenty of time for discussion, plus my extra slide full of crap like that if anyone's interested. Oh yeah, I'll just explain what this is. The title is a line of PHP, and the body is, so the leftmost column there corresponds to lines of HHPC. So string, bpassc, fcall built-in, unboxr, and setm are all HHPC opcodes. All the rest is HHIR. Briefly, what this is doing, you push the string onto the stack, pass it as an argument, call the function stir to upper, which is a built-in, unbox the result. We actually shouldn't be doing that because, anyway, we have work to do. And then setm, which is putting an element into an array. This is pre-optimization, by the way, so you can see some dumb things like if you look at the lines numbered 17 and 18, we incref a thing and then decref the same thing. So that's entirely useless. Yeah?
So I'm the kind of guy who doesn't get out and out with the Java virtual machine spec. Where do I get it? Is the specification of GitHub Java virtual machine spec?
Yes.
I could repeat that on here, but well, for the benefit of the Hangout, I'm just asking where you get the spec of the virtual machine, so you can learn about the implementation.
It is included in the code base, which you can get from GitHub.
So there isn't like a PDF, like here's the
No.
virtual machine spec.
It's a text file in the Git repo.
Okay. Do you know how? I mean, have you seen the Java spec? Can you sort of contrast how this compares?
I don't know how terrible this is to admit, but I've never read the Java spec.
Okay.
So I don't know what it looks like.
I think there's a lot of similarities. First of all, both of them are stack-based machines, and second of all, they're both tailored to a particular language. The bytecodes for Java, for the JVM are tailored for the Java language, and here we're tailored for PHP. But that's about it. the rest is very different. Details are very, very different. For example, PHP is dynamically typed, so the bytecodes are dynamically typed also. You saw node typing there. That's one of the primary differences we have.
Just did a little bit of a backstory in,
So
if
there's
you
a
want
lot
to
of
give the backstory.
text, then it describes instructions way down here somewhere. So like
Is it
these
worth just giving a backstory on hip hop? Because I'm curious to.
backstory.
cares about
Okay,
that.
so I should have led off with this, I guess. You may have heard of hip hop as a thing that transforms PHP to C++, and that is how it originally started way back in. Oh man, this must have been late 2008. This is before I even joined Facebook. It started as someone's side project. He thought, hey, you know, C++ compilers are pretty good. C++ and PHP are kind of similar, which is a crazy statement when you think about it a little more. Let's try translating PHP to C++ and compiling it and see what happens. And it was crazy enough to work. In, what was it, late 2009, we were basically running the entire site on this thing. On the side, we had to have an interpreter because the behavior was actually kind of divergent from Zend PHP, enough that it was actually causing bugs where developers would be using Zend PHP for their personal sandboxes, committing code that behaved differently in HPHP, or HipHop. We call it HPHP internally. I'm probably going to slip up and say that several more times. Anyway, they would commit code that behaved one way in their sandboxes and turned out to behave differently in production. This caused bugs. Was not a sustainable situation. So we hacked together a single pass interpreter called HPHPI, which just evaluated an AST. Later on, I'm still not sure of the timeline for this. I think this was late 2010. The idea of doing a proper bytecode virtual machine in JIT came up. And that's what we worked on for, actually the team was split, working half on HPHPC, the C++ compiler, and Hsvm for most of 2011. Sort of mid-2011, the bytecode interpreter got to a point where it could run the site. Sort of mid-2012, I think it was, the JIT got to the point where it could run the site. I don't know.
Beginning of 2011, the JIT was
Beginning
running.
of 2011,
Yeah.
the JIT could run the site?
Mm-hmm.
Okay, I must be off by
We
one in
spent
my
all of
years.
2011 performance tuning the JIT.
Oh, the performance thing, yeah. So once the JIT could run the site, it ran the site way slower than HPHPC, and it took the next year to get it up to performance parity. Now, the entire site runs on Hsvm JIT. HPHPC, the C++ thingy, is retired, and it's being deleted from the code base as we speak. So Hsvm is all that remains and is the focus of all of our efforts.
And one thing to add is, with a VM, we are always running as a combination of JIT and interpreter, right? So the interpreter will always be there, because some of the corner cases we don't want to handle in the JIT, doesn't make sense to handle in the JIT. We want to fall back on the interpreter. So for ARM, keep that in mind, is we're always going to have the interpreter there as well.
So can I use opcode caching with HHVM?
It has that essentially built in. If you're running, there's essentially two modes of operation. One where you convert your entire PHP code base to HHPC bytecode offline, which actually allows for some more powerful optimizations. Serialize this to disk. Ship that out to all of your servers, and then your servers run from that serialized disk file, loads it all into memory, runs out of memory. Not runs out of memory as in there's no more memory left, but operates entirely with stuff that's in memory. For other applications like developer sandboxes, we don't do this, and HHVM just reads PHP files off of disk and converts them to HHPC on the fly. and caches the HHPC in memory. So essentially, you can't turn off opcode caching in this world.
Sorry? Can you repeat what you said?
Essentially, you can't turn off opcode caching. That's just how the whole system works from the start.
So I can't use APC or eAccelerator or third-party caching?
No, you can't. You can't use a third-party opcode cache extension. The APC API is available. You can store values in there, but it doesn't apply as an opcode cache.
So any sort of benchmarking you did, I mean using Hsvm or comparison with PHP and opcode caching, any specific numbers you got improvement-wise?
I don't have specific numbers on me. We don't do much benchmarking other than, we alluded to this earlier in the questions for the last session, but the main way we measure performance improvements in HHVM is to use this system that we have internally, which basically replays recorded production traffic. So we don't regularly run any sort of micro benchmark suite. So I don't have numbers for those off the top of my head. But generally, what was this? The last time Zend PHP could run the site was sort of middle of 2010. Because after that, behavior diverged too much, which actually is not the greatest situation and something we're working on resolving. But anyway, back then, HPHPC was about a 2x CPU time, or more than 2x CPU time improvement over Zend. And HHVM now is faster than HPHPC now, or the last time we built it, which was a couple months ago. And HPHPC a couple months ago was probably about 2x faster than HPHPC 2 years ago. So the answer is much faster, depending on your workload. With the JIT on, HHVM beats Zend on pretty much all micro benchmarks, except for ones that are floating point intensive. We're not good at floating point math. With the JIT off, just running the interpreter, it's about the same as Zend.
So how much, this is another non-ARM specific HipHopVM question, but so how much does your PHP dialect deviate from the Zend version?
There's a few corners of behavior that we've explicitly decided we're going to do this differently, because mainly for performance reasons. Like doing it correctly would just, there's no way to do it without sacrificing too much performance. That's a pretty limited number of cases, and we're hoping that it doesn't affect people too much, because we do want this thing to become a credible drop-in replacement for Zend PHP. Like some hosting provider could just drop in an HHVM binary instead of their Zend PHP binary, and everything would just run. So we're missing support for extensions is the main thing. So with Zend, you can write extensions in C and plug them in. Our API for doing that is not compatible. What else? We have some other behavioral differences that we're working on cataloging right now, and they are just bugs. We do want to fix them, and we will get around to them, but right now it's a question of finding them. What else? And you know, PHP is still evolving. Like recently, what was this, version 5.3, I think, it got namespaces with the silliest syntax ever. The namespace separator is a backslash. No joke. We haven't implemented that. Yeah. But you know, if we want this to actually be a credible replacement for Zend, we have to do it. And we will, eventually. Did that answer your question, or? Yeah. Okay.
Hi, thanks. Are there any significant users of this outside of Facebook today?
Oh,
Significant as in significant, not corner case, not, single developer.
Yeah. That's kind of outside my area of expertise, but I know at one point we were working with MediaWiki to get their properties running on HPHPC, which is hard because HPHPC requires a completely different deployment process. It's instead of uploading PHP files to your server, you get all your PHP files together, run them through this thing, get a whole bunch of C++ files, and then somewhere find the CPU cycles to run all of those through G++. I think we are working with, we are making sure that, we have verified WordPress with which Hsvm JIT. I don't know if we're working directly with them or with MediaWiki or with any of the large PHP shops like that, but we certainly would be open to it. So I'm not sure if I've answered your question, or I actually don't know on the present day what happens when you go to Wikipedia. I don't know what they're running, but we would like to get to a world where they are or could be running Hsvm JIT with little trouble.
Any more questions?
How much time does it take to compile HipHopVM? Oh boy. Internally, we use distcc with, so we just type make -j and let distcc handle it, and that takes something like 2 to 3 minutes maybe, from 5 minutes from starting from a completely clean tree. If you don't have distcc and you compile all the files one by one, then it takes hours. But I usually don't do that. Yeah.
Is there any compliance test, that will compare HipHop with general PHP?
Sorry, could you speak up?
Any compliance tests to make sure what is covered?
Oh, we used to run Zen's test suite. We haven't done that in a long time. I don't actually know why. I think we might be working on doing that again, because that is certainly a useful way of fleshing out behavioral differences. All right, if that's it. All right, thanks everybody.